Hello, everybody. My name is Kevin. I'm a software engineer at Datadog, and I'm here with you today to talk about pushing C# to new places with Native AOT. So let's start by explaining what is Native AOT. You probably already know that .NET assemblies are compiled to IL code, and then at runtime, when they are called for the first time, the JIT compiler is going to kick in and convert them to native assembly. This works fine, but it has a few drawbacks, and the main one is that it's going to increase the loading time of your application quite a bit. So to get around that, there are tools available, Engine for .NET Framework and ReadyToRun for .NET Core, which allow you to perform this step at compilation time. So your methods are compiled ahead of time to reduce the startup time. And Native AOT goes one step further, and it compiles your application as a single standalone native library. So the difference between Native AOT and ReadyToRun is not easy to understand. So let's try to explain it. Basically, when you use ReadyToRun, you are going to produce a .NET assembly which contain the functions compiled ahead of time. But apart from that, it's just a traditional assembly. So it's going to contain IL plus a native code, and it's going to behave exactly like a normal .NET assembly. And so you can do everything that you could normally do, like load it dynamically, emitting dynamic code, and so on. There is really no other difference with a normal .NET assembly, except that it contains native code. On the other hand, Native AOT is going to produce a native library. And so you are going to have exactly the same limitation as a native library. And there is no IL at all inside of it. In fact, there is not even the JIT compiler. And because of that, you cannot load another .NET assembly in your Native AOT application. You can reference .NET assembly at compilation time, but at runtime, you cannot decide to dynamically load an assembly. And likewise, you can't emit dynamic code at runtime because you don't have a JIT compiler. So you can only do what a native application could do. So why would you want that at all? Well, there are a few benefits. So the first one is faster startup time, but I don't know if it's actually faster than ReadyToRun. The other is lower memory usage because there is no IL and no JIT compiler. So binaries are going to be much smaller, which means that you are going to save on disk space and in memory. And you have a better native interoperability, which is a subject of this talk. And so to illustrate this point, we are going to try to write a .NET profiler in .NET. And this is something that was impossible before. You couldn't do that in classic .NET. And I'm going to explain why. But first, let's have a look at the .NET Profiler API. So basically, to write a profiler, you need to export a DLL getClassObject function, which is expected to return an instance of iClassFactory. Then iClassFactory will return an instance of iCoreProfiler callback. And finally, the runtime is going to call iCoreProfiler callback.initialize and give it an instance of iCoreProfiler info, and you can use that instance to interact with the profiling API. So why is it so difficult to write a profiler in .NET? Well, there are a few problems. The first one is that there are no easy way to declare DLL exports in .NET. The next one is that we're going to need to consume and expose C++ virtual objects that are part of the COM API. And the main one is that the profiler is loaded at an early stage in the lifetime of the process, at a point when the VM is not ready to execute .NET code. So let's illustrate each of those points. So the first one is that the profiler is loaded too early. So when you start your application, it's going to execute the entry point, which will trigger the initialization of the .NET runtime. And the .NET runtime comes with a bunch of components, such as the GC, the thread pool, the type system, and so on. And during that initialization, it's going to load your profiler and initialize it. But since your profiler is a .NET application, it's going to rely on the .NET runtime, but the .NET runtime is still initializing, and this is not going to work properly. On the other hand, if your .NET profiler is written with native AOT, then as I explained, native AOT applications are standalone. And by that, I mean that they come with their own runtime, so their own GC, thread pool, type system, and so on. And so the profiler is going to use its own runtime instead of relying on the one that is still initializing. So that's a problem that we don't have anymore with native AOT. Another one is that the profiler would end up profiling itself if it were written in .NET. So basically, let's say that in the profile application, you execute a .NET method. The first time it's called is going to trigger the JIT compiler. And when the JIT compiler compiles a method, it raises an event on the profiling API, which is JIT compilation started. But since the event handler is in the profiler and the profiler is written in .NET, so the first time it's going to be executed, it's going to call the JIT compiler to compile it. And because we are calling the JIT compiler, it's going to raise the JIT compilation started event. But to execute the event handler, we need to call into the JIT compiler, and so on and so forth. And so we have an infinite loop there. So once again, this is a problem that we don't have with native AOT. First, because all the methods are compiled ahead of time, and also because native AOT comes with its own runtime. Okay, so the next problem is to declare a native export. So let's start by explaining what are native exports. So I don't know if you've ever wondered how DLL files work. Basically, how is it possible to load an arbitrary file and execute functions from it? And the trick is in the header. It's a PE header for portable executable, and the format is well-defined, and inside of it, you will find the export table. And the export table will contain various information, such as the name of the functions exported by your DLL and their location inside of the file. And so by combining those two information, you can conclude that at that part of the DLL file, you have my function, and at that part, you have do stuff. And so then calling code from a DLL is just a matter of mapping the file in memory and then jumping to the location of the function you want to execute. So of course, in practice, it's more complex than that, but this is the concept behind it. And so we're going to need to declare native exports. But the problem is that native exports are not supported by C#. But fortunately, they are supported at the IL level. And so on classic.NET, there was a trick, which was to use, first to compile your application, then use IL-DSM to decompile your assembly into IL, and then add your native exports, and then recompile it using IL-ASM. And there is, for instance, the unmanaged exports NuGet package that does exactly that. But it's a bit complex, and sometimes it fails, and you don't really understand why. But fortunately, with native AOT, this is directly supported at the C# level. And so you just need to add the unmanaged colors only attribute to a method, and it will automatically generate a native export. So that's one less thing to worry about. Last but not least, we need to consume and expose C++ virtual object. So what is so special about virtual object? So let's take a simple C++ object. In memory, it's going to look like this. And then let's say that we add a virtual method to the object. So what is going to happen is that the compiler will emit a hidden field at the beginning of the object, and that field will be a pointer to the vtable. And the vtable is a chunk of memory which will contain addresses of the implementation of the methods. And so if we add another method, something else, this will add another entry in the vtable, which will point to the implementation of something else. And then if you declare another object that inherits from my object, with which overrides the virtual methods, just like before, it's going to contain a pointer to the vtable as the first field, but this is going to be a different vtable because it will contain the implementation of the child method. And so thanks to that, whenever you are calling a method on a virtual object, this is not going to be compiled as a direct call, but rather as an indirect call through the vtable. And thanks to that, code that is capable of calling do something on an instance of my object will just work the same on an instance of child. And so in our case, we need to export an instance of iClass factory, which contains virtual method. And so for C++ to be able to use our object, we're going to mimic the layout of a C++ virtual object. And so basically, in memory, somewhere we will have the implementation of all the method in .NET. And so we're going to allocate a chunk of memory that we're going to fill with pointers to all those methods. So that will be our fake vtable. And then we are going to allocate another chunk of memory, which will contain a pointer to that vtable, and that will be our fake instance. All right, so it's time to switch to the code. So let me grab my Visual Studio instance. It's right there. So I have a project for my profiler, and it's a class library project that is targeting .NET 7. And inside of it, I set the publish AOT property to true, which tells the compiler that I intend to publish my project with native AOT. And so it will generate specialized warnings whenever I do something that is unsafe. And also I set a natively to shared to say that I want a shared library, but that's something that you can give on the command line when publishing your project. And I will have a test application, which is just a console application where I display hello world, I wait to press return, and then I throw an exception. So I start by adding a DLL main class, and inside I declare my DLL get class object method, and I add the unmanaged colors only attribute to export it. And now here I have this pointer, and I need to assign it to an instance of class factory. And so we will start by declaring a C# object. So here is my class factory. And now I need to create my fake virtual C++ object so that the runtime can use it. But the thing is, it's not possible for the native runtime to call those methods because .NET method use a different calling convention from native methods. And so to get around that, we need to declare additional methods. So I just put them in a nested class to avoid name conflicts. And I decorate them with the unmanaged colors only attribute. And this tells .NET that those functions will be called by native code. And so they are compiled with calling conventions that are compatible with a native code. And if you are not happy with the default calling convention, you can override them. You can set the one you want in the attributes. One subtlety here. So here my query interface method has an in parameter and an out. But whenever you use unmanaged colors only, you are not allowed to use in and out. This is going to be a compilation error. So instead, we are going to use pointers and do some gymnastics to mimic what in and out are doing. Okay, so now that I have my method, I need to allocate my vtable. So I'm going to declare a constructor. And inside of my constructor, I'm going to allocate a chunk of memory, of native memory. And it will be big enough to contain 5 pointers. 5 because I have 5 methods. And then I populate my vtable with the addresses of all the static function here. So with that, I have my vtable. Now I need to create my fake instance. So I'm going to allocate another chunk of memory like this. So this time big enough to store 1 pointer. And I'm going to assign a pointer to the vtable. And finally, I'm going to store the address of my fake object so that I can use it later. But here we still have a problem. Basically, I've set the address of my static unmanaged colors only functions. So those ones are going to be called, but I want to execute those ones. So when I'm here, I need somehow to call this method. But the problem is that you can only use unmanaged callers only on a static method. And so I need somehow to fetch my instance of class factory. And for that, I'm going to use my fake C++ object. So basically, I have here a pointer to my fake object. And so basically, if you remember, my object is looking like that, and I'm going to add, and so yeah, so somewhere in memory, I have my instance of class factory. And so I'm going to add a field to my fake C++ object with a pointer to my instance of class factory. And thanks to that, I will be able to retrieve it from my static function and call the instance function. And so basically what I need to do is here allocate enough size for 2 pointers. And basically for the second pointer, I just need to set the address of this object. But I'm not allowed to do that. And the reason is that the address of managed objects can change if they are moved by the garbage collector. And so it's unsafe to take the address of a managed object. Fortunately, there is a way around that, and that way is to allocate a GC handle that is going to wrap my instance. And then there is a very convenient API that is GC handle.toInPointer, which is going to take my handle. And basically, it's going to return a pointer that will later allow me to retrieve my handle. And so then in the query interface method, I can retrieve the pointer to my handle, then use GC handle.fromInPointer to retrieve my GC handle. And when I have the handle, I just need to use a target property to retrieve my instance of class factory. And then when I have my instance, I just need to call my managed query interface method and just do some gymnastic because, as I explained, I cannot declare out parameter on my unmanaged callers method. Yeah, and return result. And that's about it. Then I need to do that for every method, so I'm going to copy paste it. And from there, I have everything for my fake C++ instance to work. So now in my DLG class object, I'm going to add a static field to store my instance of class factory, so factory. And then when the runtime call DLG class object, I instantiate it and I return a pointer to it, factory.object. Sorry, factory.object. All right. So let's try to test it. So I'm going to publish my my project, and I will launch my my console application by setting the environment variable, which will tell .NET to use my my profiler basically. Compilation of native code takes a bit longer than just a classic C# project, unfortunately. And now, if I launch my console application with a profiler, you can see here the hello world. But before that, we can see that DLG class object was called, and then the create instance method of my class factory was called. So it looks like this is working. So then my class factory is expected to return an instance of iCoreProfiler callback. And so all I have to do is do the same boilerplate code for the iCoreProfiler callback interface. But if you look at it, you will see that it has a lot, and I mean a lot, of methods. And so there is no way that I'm going to write all this boilerplate code for all these methods. So instead, what I did is I wrote a sort generator. So I'm not going to explain how it works, but it's going to generate exactly the code that I showed you. So basically, I declare a iClass factory interface, and I decorate it with a native object attribute, which will instruct my sort generator to generate the boilerplate code. And now what I can do here is to implement iClass factory. Then I can, let's copy paste it. Basically, instead of doing all of this, I just call my wrapper that was automatically generated, and I can remove all those exports, and this will work the same way. Okay, so now to implement ICOProfiler callback. So ahead of time, I've prepared the interface, and now I just let ReSharper implement it. So yeah, 80 methods, there we go. And now I just add the bit of code to use the wrapper that was generated by the source generator. And then, yeah, in my class factory, I still need to return that instance. So here I'm going to add a field to store it. So here is my callback. And whenever the runtime call create instance right there, I just create a new instance of CoProfiler callback and return my fake C++ object. After that, the runtime is going to call query interface. So why is that? If you look at the documentation, you can see that there are many versions of the ICOProfiler callback interface, and each one of them has a GUID associated to it. And so the runtime is going to call query interface and give me the GUID of each of the interface. And when I find the one that I support, so when I find ICOProfiler callback 2, I'm going to return it through the out parameter. So likewise, I'm going to copy paste this. So basically, I check the GUID that I was given, and if it's the one I expect for ICOProfiler callback 2, I assign my fake instance to the out pointer. Otherwise, I return the error code saying that I don't support this interface. And then finally, the runtime will call initialize and give me an unknown object. And then I need to interrogate that unknown object to fetch the instance of ICOProfiler info. So just like before, there are many instances of ICOProfiler info. And so I call query interface with the GUID of the interface I'm interested in, and query interface will return it to me. And so here we have the opposite problem. Until now, we have created fake C++ objects and given them to the runtime. And now the runtime is giving us a C++ object, and we need to call a method from it. So for that, I'm going to implement a wrapper. So here it's a wrapper around unknown. And basically, I create it with a pointer to the C++ object. And the first thing I do is read the first field of that object to fetch the vtable. And then for each of the methods of my interface, I look into the vtable to have the address of the function that implements it. And then I just cast it to a function pointer and call it. And so from there, in my initialize method, I'm going to copy paste it. There we go. I just create my wrapper with the object that is given to me. I call query interface to fetch ICOProfiler info 3, and then I check the result code to see if it worked. And so just like before, I added a source generator to avoid writing all this boilerplate code by hand. And so there it is, and it's going to generate the same object as I showed you. All right. And I store the instance of ICOProfiler info, and now I have everything I need to use the profiling API. So basically what we're going to do is our profiler will listen for exception in the target application, and when there is one, we are going to dump the call stack, just to show that the profiling API works. So I call setEventMask on CoProfiler info, telling it that I want to be notified whenever an exception is thrown, and I want to have the capability to work the stack. And then in the exceptions thrown event, there we go. I'm going to copy paste a bunch of code. There it is. And so and I'm going to compile it. Sorry, here. All right. So I'm not going to explain in details what it does, because here I'm just using the profiling API. So you will need a talk explaining you how the profiling API works. But from a native interoperability perspective, I'm not introducing any new concepts. I'm just calling the APIs on the core profiler info object that we created previously. The profiling API is quite complex. Sorry. And so, for instance, you can see that here, all this code is only to work the stack. So really explaining what is going on here will be a talk of its own. All right, with that, it has finished compiling, sorry. And now if I launch my application, so here what we can see is that the runtime did call curl interface with a lot of different grids. And here I recognize the one for iCore profiler callback 2. And then the runtime called initialize, and we were able to successfully fetch our instance of iCore profiler info. Then we have hello world. I press return to throw the exception. We can see that the exception thrown event was raised. I was able to find the type of the exception, and I was able to dump the call stack. And so we have confirmed that it is now possible, thanks to Native AOT, to write a profiler entirely in C#. So that's it. If you want additional resources, the source code for this project is on GitHub on the .NET Conf 2022 repository. And I also have a dedicated repository for the profiler, because I intend to keep working on it in the future. Don't hesitate to check my blog if you are interested in knowing more information about how it works, and also fun stories about debugging weird bugs. And don't hesitate to ping me on Twitter if you have any question. And thank you for your attention.